meter square and times y bar start. So that one from here to here. And that one, that number is, if you figure out that carefully, 0.417. So that means 41.7. So 0.0417. So that is a meter to the cube. Okay. So AY bar, this one is 83.4 times 10 to the 6 meter cube. So we plug in that number here. So 83.4 times 10 to the minus 6 meter cube. And I is 8.63 times 10 to the minus 6 meter to the 4th. And T, what is T? T is the thickness at the level here. So here. Okay. For the I-beam, once we cut, they only cut that one. So that one is 0.06 meters. Okay, so this calculation, I didn't give you, this one is 20 millimeters. The weight of the fringe is 20, so this is 0.2. So that one will be 725 kPa. So this calculation will give us the information about the AA is that much, and the around of the space. Can I erase this part? I erase this part. So now I want to show you the direction of the shear stress. So let me enlarge the drawing here. So along this edge, AA, locally the shear stress is like this. The shear stress is induced by transverse loading. So on this side, the transverse loading is working downward. So the average shear stress will be the same thing here. Along this edge, that will be downward. Okay. And if we expose this one into 3D view, let me take away this one. Okay, so basically I take the top web away. So here I want to show you clearly. So along this edge, this is the shear stress. So inside this level, the shear stress will be in that direction. Because the concept is this: if you will be able to pick this small element, so on this small element, this edge is here. And that one is will be calculated shear stress like this. And then again, using our chapter 1, once we know the shear stress on one side, then on the other three sides, we can right away to draw the shear stress like this one. So this side is the top, so that one goes inward. Okay. Another side, we'll look at what's going on for this part and the bottom of of that one. So let me put into the 3D of this one for this case. So that case, the top one will be like this, and the 3D view is like this. So to the bottom, let me put into in different view like this. So right now I pick up this one and I expose his bottom side. So let me pick in this way. So that is the AA. Okay. So that is the interface to this side. So that is the interface. Let me highlight in this case. Are we okay? Okay. And now again, and on the AA, what being calculated is the strain stress is on this side is like this. Okay. So in this way, if we pick up the small element like this. Okay, so in this way, that small element, no, sorry, let me pick this element.
What direction, I'm having to tell you what direction your force arrows there in the red are going. Are those downwards or back?
This representing is the cap on the top, okay, and this one representing is this side, and this one representing is this side.
I'm just trying to determine, are those arrows going horizontally or
yes,
vertically? It's
yeah.
difficult to see
Okay.
the picture.
Okay. So on this side, that was vertically on this side, on this face. Okay. And then I pick up this element like this. No, not a good way. Let me redo it again. Which element I should take? It seems I have hard time to look at this one. Let me redraw this one. I have hard time to visualize, not to mention it. So for this one,
well, it's going to need to go into the top rectangle, right?
yes.
Into the board.
I think the best way I have to draw it is in this direction. Okay, that is the best direction we can see it. So this one going to there. Okay, so that would be the better view. So basically here, and on this side, this is the average strain stress. So again, this is the average strain stress like this. And now let me pick up this element. Okay, for example, for this element here,
Is that element the same one that you picked previously?
yes.
Okay.
So this edge is this edge. Okay. And then in this way, on this edge, that is the strain stress, right? On this side. So once again, once we know the strain stress on one side, we would know the strain stress on the other three sides like this. So which means the strain stress on the top would be pointing like this. Right?
Isn't that just the same thing you just drew?
No. No, not in this.
You're looking at the.
Let me do this one one more time. Okay, right now we concerned is this block. Let me highlight the block. So we concerned in this block. And now I want to see is what is the distribution of the shear stress in this area of that block. Okay, so that means for in this block, the shear stress along this side, this is the bottom side of this block, so the shear stress is pointing downward to that edge. Previously, I draw the shear stress is outside the domain of the interest. It doesn't exist. So here I draw the shear stress. Basically here locally is applying to that one. Okay, so now for this case, then I can pick up the element is how to pick up that element is really hard to draw it. So for example here, what I want to do is I make a cut. And on this cut, I make the element, I pick the element like this. Can you see it? Basically that element is kind of cutting into this block, okay?
So it's not on the front plane, it's on the side?
Is not at the front, is get into this direction.
Yeah.
Okay. Okay, now on that element, let me put into in the same orientation like this. Okay. So this is this side here. And this edge corresponding is this edge. And on that edge, we have the distribution of the shearing is like this, top. So then on that three sides, we have the shear stress like this. And then the bottom side here corresponding is a portion at here, right? So that means in this area of concern, the shear stress actually working is toward that way. Okay. So the conclusion is this. This area is the same as this is, let me call this is the interface. This interface is the same as this one. Okay, if we pick up from this viewpoint, the shear stress on this interface going that direction. On the other side, at the action reaction, we have the same magnitude of the shear stress, but they're working on the opposite direction to this viewpoint. That's it. Okay, so basically here, the conclusion is this. Really doesn't matter once you get into the detailed viewing of the direction of the shear force or shear flow or the shear stress, then the direction really depends on is the viewpoint of your pick. And that one is precisely determined by this one here. As long as we know the direction of the shear stress, and then from there we can translate into this interface, like from this viewpoint or from this viewpoint. And since in this demonstration, this will be easier, right? Okay. So from here, I tell you is how to calculate the magnitude, and also tell you how to justify the direction of the shear. And in these chapters, most of the time we concern is about the magnitude. As far as the direction, no. But here I give you more information. Okay, so, and now we're back to the BD.
So the 725 kPa is going along the top. That's the shearing at the top, or is that the vertical?
For this case, basically each magnitude of the force is 725.
Okay.
Okay, and then for this case, this is a certain strain stress. This is a strain stress acting on this plane. This is a strain stress acting on that plane, and both are not the same quantity. They both are not the same entity. Okay, again, the strain stress. When we talk about the stress is the average force acting on plane. So depends on which plane, which direction you talk about, and that is a different quantity, different entity of the stress components. Okay, back to the chapter 9, the chapter 1. X, Y, Z. For example, here, this is tau acting in this plane is a y plane. This plane has the normal to y, so there's a y plane pointing to the z direction, so there's a tau yz. And for this component, this is tau in the z plane pointing to y direction. They have the same magnitudes, but they are not the same entity. The same concept to here. This is the one stress. This is the one strain stress component. This is another stress component. By chance, not by chance, by static equilibrium, they just have the same magnitude, 725. Yeah. Okay. So basically, you got 1 for 4. So now we're back to continue to calculate B. So at B, the tau average along BB will be equal to the same calculations, 150 newtons. Q will be, right now for the Q is this one, and this is our neutral axis. So this is the centroid of the shaded area because this is a BB. And for the shaded area, yes?
When you get 1 for 4, is that something that always happens in this situation?
1 for 4, that is always be the like this case as long as everything is in static equilibrium. Okay, so that is happening in our class. Okay, in mechanics material in this class, this is always true. So Q for BB is this. This area. Do I have that one? Let me label it here. Okay. So this is the BB, and we pick the shaded area is this. From the level of the interest, we either pick either side. Okay, either sides of the whole entire cross section. For example, here, let me pick this side.
Could you technically do the same with?
The same magnitude will be the same.
The magnitude will be the same.
I will show you later on. Okay. So let me pick this one. So the Q for BB will be equal to the area 0.06 times 0.02 and times this one. That one is 58.3 meter. 58.3 millimeter. So that is 0.0583. So meter to the cube. For this one number is 70 times 10 to the minus 4, minus 6 meter 3. So 70. And I, 8.63. And T, what is T? T is the width of that section of that level. How much? 0.02. So for this case, that being calculated is 608 kPa.
Why is it 0.02 for all?
Because